Elastoplasticity is the nonlinear stress-strain relationship shown by the materials beyond the yield strength of the material. Many materials, when stressed beyond the yield strength, show elastoplasticity. Beyond the yield strength of the material, further loading results in the permanent deformation. This is known as the plastic deformation. Stress-strain relation in the elastic and plastic region may be linear, multilinear, or nonlinear. An example of an elastoplastic material behavior is shown in the figure below. The relation between stress and strain is linear up to 0.1% strain. It becomes nonlinear with higher strains. After the yield stress of 195 megapascals, plastic deformation takes place. In the elastic region, the elastic modulus relates stress to strain. Similarly, in the plastic region, the tangent modulus relates the stress to the plastic strain. Note that the tangent modulus is often significantly small compared to the elastic modulus of the material. Before moving forward, it is important to understand some theoretical concepts of elastoplasticity. As we saw in the previous slides, elastoplasticity involves plastic deformation in the structure when stressed beyond the yield strength of the material. This yield strength is obtained from tensile or compressive testing of the material. These material tests generally involve unidirectional loading. This results in stress only in one direction. An example of a tensile test machine is shown in the picture below. The stress-strain curve generated for a steel sample is also shown in the graph. However, in the most real-life engineering structures, the loading is far more complex than the unidirectional loading. Most structures experience loads in multiple directions at the same time. This results in different magnitudes of stresses in different directions. This condition is known as the multi-axial stress state. Appropriate criteria is required to compare uniaxial strength measurements with the multi-axial stress state. One of the ways of converting a multi-axial stress state to a single stress number for comparison is von Mises stress. In the last slide, we saw that there needs to be a way to compare a multi-axial stress state with the single-valued material yield strength. One of the ways is to use the von Mises stress for comparison. Von Mises stress is a single number representation of a multi-axial stress state that will have 6 components of stresses. The 6 components include 3 axial components and 3 shear components. Equation of calculating the von Mises stress is given below. This equation can be graphically represented using a cylindrical surface, as shown in the figure. The radius of this cylinder is equal to the yield strength of the material. Physically, yield cylinder represents all the possible combinations of the 3 normal stresses, sigma 1, sigma 2, sigma 3, and the 3 shear stresses, sigma 1, 2, sigma 2 3, sigma 3 1, such that the von Mises stress calculated using above relation is equal to the yield strength of the material. When von Mises stress is equal to the yield strength of the material, it means that the strain energy in the material is enough to permanently deform the structure. This allows the multi-axial stress state to be compared with the uni-axial yield strength by using von Mises yield criteria. Note that von Mises is one of the many yield criteria